So let us finish this chapter 13, which is equilibrium and human movement. And we have two examples that we would like to solve today. One of them will be extended into a bigger problem, which is identifying the center of mass for the human body. And we're going to identify the center of mass ourselves. Let us continue with the center of gravity and the center of mass. What is the center of gravity? Remember in the statics and dynamics, you learned about the center of mass and center of gravity and something called the centroid. The center of mass and the center of gravity are the same because it's the point in the body that is all forces at equilibrium, which means at zero, and all moments should be at zero. Now the centroid is something that we don't use much in human motion analysis or in biomechanics. So the center of gravity is the point around which body weights is equally balanced in all directions, and also referred as the center of mass or the mass centroid, need not to be physically located inside the body. Why is the center of gravity or center of mass of interest in the study of human biomechanics? It serves as index of total body motion. It's the point that we can track as that's the point that's moving. If you have a body like this, and I told you that we have the center of mass is this blue point, if the body is moving anywhere, we are tracking that point. It's an index. The body responds to external forces as all mass works concentrated in the center of gravity. That's another reason why we want to identify the center of gravity or center of mass. And when a weight vector is drawn for an object in as a free body diagram, everything should be displayed on the center of mass, right, or center of gravity. Center of mass, if you're dealing with kilograms, center of gravity is if you're dealing with weights, right, which is the newtons. This schematic shows you different objects with their center of mass located. So you can see that the center of mass does not need to be on the object itself. So see this, what do you call it? This is the golf club. See the center of mass is outside the object. So the center of gravity or center of mass is the single point associated with a body around which the body weight is equally balanced in all directions. With movement, the center of mass changes its height. For example, if the center of gravity of a skilled high jumper may pass under the body during the jump. In biomechanics, we would like to identify the human body center of gravity or center of mass. Now, this is not an easy task. Why is it not an easy task? First, our body contains two or more movable interconnected segments. We said we're going to model our human body as a multi-segment coupled pendulum system. Now, every time the body changes its configuration, the weight distribution and the center of gravity location changes. And remember, the center of gravity and center of mass try to follow heavier objects. That's one problem. The other problem is the location of the center of gravity of human body is complicated by the fact that its constituents, you remember we have bone, muscles, and we have fat. They have different densities and they are unequally distributed throughout the body. Now that's another problem for us to identify the center of mass or center of gravity. Make sense? Because we have different masses and densities for different tissue. We have two ways to solve this problem. We can use something called the balancing method in identifying the center of mass, or we can do something called the segmental method. What you're going to be doing in the lab 2 weeks from now is we're going to be using the segmental method in order to identify the center of gravity for the human body. That's very important. And this is a research problem and an idea. Let's say that you know the football players, they wear all these gears on them. What is the effect of the gears that a player is going to be using on the center of mass or the center of gravity? Does it make sense? So it's very important for us to identify the center of gravity all the time. So I'm going to solve two problems. One using the balancing method and one using the segmental method. So let's start with the first one, the balancing method. So this is, I think Bernoulli is the one who came up with this because he was famous in using weights and masses. So here's the question. In order to be able to find the center of gravity, I need to use a board, a balancing board. See this board here, these 2 points? This is the balancing board. And you can get a subject. One side of the board you put a scale, and the other side you just put a reaction, anvil that is just holding the forces. And then you can see, using the analysis of the moment, I can find actually the center of gravity because around it, all forces and moments should be equal to zero. Does that make sense? So here's my question. we would like to find the distance from the platform support to the subject, given the following information of the diagram. So we have the mass of the subject, 73 kilograms. Does it make sense? Now, here's the first thing we need to do. How much weight is that? So the weight of the subject or the patient, how much is that? 73 multiplied, you would like to find the weight of the subject. So 73 multiplied by the acceleration of the gravity, right? So that's 9.81. Make sense? How much is that? And we need to find the weight of the board. We'll do 716 newtons. Make sense? Now, the weight of the board is 44 multiplied also by 9.81. How much is that? 431 newtons, right? Now, the scale reading, so if the subject is laying on top of the board, the scale here is, which means that this is the weight that is acting on this point, right? Correct? So it's 66 kilograms. So how much force or weight? What is the weight of the scale? Which is I'm going to be calling it reactive force 2. Correct? Right? Remember, it's reactive force because that's how much it's pushing back. So the reactive force 2, RF2, is how much? Is 66 multiplied by 9.81. Does it make sense? Right? So how much is that? 647 newtons. We good? Now, so if I want to put this all in on this graph, do I know how much is the reactive force 1? No. Correct? Now, do I know how much is the weight of the board? Yes. And that is 341, correct? Oh, sorry, you're right. Thank you. So that's 431 newtons, right? And how much is my reaction force? 647. And how much is the weight of the patient going down? That is 716, right? Does that make sense? Now, so here's what I want from you. Can you formulate, now if I would like to solve this as to find the distance, which see the distance D? The distance D is where the weight should go down, and that's where what I would like to identify, because that's the center where the center of mass is around it, correct? That's where you put the weight. We said that the center of gravity or center of mass is where you put the weight on the free body diagram. So that's my D. Now, if I would like to solve this as torque or a moment problem, you need to formulate an equation for the moment where the summation of all moments should equal to 0, correct? That's what we said. So which point you would like to solve around? You will find the point that you have the largest number of unknown to eliminate it, right? Because the distance is 0 and we don't want to have that. So I will pick point A here. So I will say, can we find the summation of moments around point A? They should equal to 0 because we're at equilibrium, assuming that counterclockwise is positive. Does that make sense? Okay, I will give you. Give you a couple of minutes to see if you can formulate the momentum equation. Remember, how many forces do you have? You have first reaction force, second the weight of the board, that's 3, and you have a fourth one, that's force, but it's passing through the point, which means that the distance is, I don't have any moment here. Yeah, on a piece of paper. Yeah. Okay, so I would want from you to formulate the equation of equilibrium, which is the moment equation of equilibrium, around point A, and the summation of moment should equal to 0. And pay attention to the direction, right? Counterclockwise is positive because the positive and negative makes a big difference now. And here's the thing. Let's assume this. See this I here from this point to that point. Let's assume this to be 2 meters, and you need to find D, right? So assume the distance between the two anvils of the board to be 2 meters. This could be a cool capstone project actually to build this setup and use Arduino to give you where is the location of the center of mass. Anyone can confirm it's 12 meters? Oh no, it's not 12 meters. How come? Well, that thing is called. It's 1.2. 1.2. Perfect. Yeah, this is a very important application of moment and equilibrium. So let me show you how would I do this. Thank you, Brian. So here's what will happen. So I would like to formulate my equation of equilibrium, which is the moment. I don't care about the forces now. So what we will do, we will say summation of moments equal to 0 around point A, right? So RF1, the reactive force, it's going to be passing through A, so there is no distance. There's no way for that thing to have moment. Now, the weight of the board is going to be this way, correct? Is this positive or negative? That's negative. So you will be saying that, well, minus W of the board multiplied by the distance. How much is the distance between the middle of the board and this point? We said it's all 2 meters. The middle of the board, if it's an engineered board, it has to be in the middle. So it has to be 1. correct? Because that's the board. That's an engineered so this point, between this point and that point, should be half of the 2, which is 1. So you multiply it by 1. Now, the weight of the patient, it should go also this way. So it's going to be rotating also clockwise, which is negative. So the first one, then it should be negative, right? So that's down, that's negative. So minus the weight of the patient. Now, do I know the distance between the center of mass of the patient and that point A? No, that's D. That's unknown. So I'll put it D. Does that make sense? Because we don't know that. Here's what happened. See this patient, if he slides up toward the scale, that is going to change my D and the center of mass. So we need to identify that. Now, I have another force, which is the third force, which is the reaction force F2, right? That is going this way, around the point, around my A. So that's going to be counterclockwise, so that's positive. So plus the RF2 multiplied by what? It's 2 meters, correct? So that's 2. Do I have any other force? That's it. All of them should equal to 0, right? That's the summation of moment around A equals to 0. Does that make sense? How we'll look at this? Now, if you do the calculations now using the numbers, so those are the weights in newtons, 716, 431, 646. That checks with our calculations. If you do RF2, which is the 674 multiplied by, that's this one, you multiply it by the distance, which is 2, minus the weight of the patient, multiplied by D that I don't know. That's negative because it is going to be clockwise. These two are negatives. And then you have the half of the 2 meters for the weight of the board. And if you move, so you move the 716 multiplied by D to the other side here, it becomes positive, right? And you keep everything on the other side. So you have 647 multiplied by 2 minus 431 multiplied by 1, right? And then how much is the one, these two? How much? Subtract 863. Yeah. And then, so that's 716D, right? Now multiply everything by 7616. You end up with D equals 1.2 meters. Does that make sense? Does it look good? Yep. So this is the way that we can use this Bernoulli board in order to calculate. So that's the first way in finding the center of gravity. Does that make sense? It would be cool actually if we can build this as a capstone project, and you connect it to an Arduino, so that it can give you immediately how much distance from the into D. It's really cool. Any questions about this? So that's the first way of identifying the center of gravity. Now, the second way, which is the segmental method, and I want you to pay attention to this one because we're going to use it in the lab on a larger scale to find the center of gravity for upper and lower extremities and the entire body. So let's say I have the hand, and it is placed in you're looking at into sagittal plane, and I provided you the center of gravity of each segment of the hand. So this is the center of gravity of the upper arm, this is center of gravity of the lower arm, and this is the center of gravity of the hand itself, right? Does that make sense? Now, the way in which that we can do this is you need to multiply the masses. So you build a table. That's something very important to do actually in the exam. If I ask you to do this in the exam, you build a table. The first column will be the segment. So I have upper arm, forearm, and I have a hand. Make sense? And then you put another row that you can show the summation, the additions. The first column, you put the percentage of the mass of the arm, of each one of those. So let's say the upper arm is 0.45% of the entire body of the weight of the body, or the mass of the body. This is 0.43% of the mass of the body, and that's 0.12%. So if I did this, I'm assuming that the entire body, how much is the entire body going to be? 1. Oh, I'm going to give you a table. There is a table. Yes. And I will give you also, I'm also going to give you distances, locations, because we need the location. And remember the big table, the chapter that we had all these measurements of the upper and lower extremities? It's from there. So I'm going to give you this. Now, what you need to do here is you need to identify the X position of each one of the upper arm, forearm, hand, and the hand mass point, center of mass. So what are you going to be filling in X? For the upper arm, it's going to be 3, correct? Right? For the forearm, the X is 5. And for the hand, it's 7. Make sense? Right? Now, you need to multiply the x position with the mass percentage. How much is 0.45 multiplied by 3? 1.35. We good? Now, how much is 0.45 multiplied by 5? 215. And 0.12 multiplied by 7? 0.84. Now, here's the thing, right? I want from you to add all of those together. You need to find the summation. So add all of this. How much is that? 1.35 plus 2.15 plus 0.84. How much? 4.34. Now, this is the summation of all the x coordinate multiplied by the mass, right? Now, here's the thing. In order to find the x of the center of gravity, you need to add all x multiplied by masses divided by the summation of masses. And for the y center of gravity, the coordinate, is the summation of all the y's multiplied by the masses divided by the summation of the masses. Because we have percentages, the entire thing is 1. So you can divide the 4.34 by 1, and that's actually your x coordinate of the center of gravity. So let's say this is 3, right? 3.34, that's here. So that's your x coordinate of the center of gravity. Can you find the x coordinate, the y coordinate? Remember, I simplified it to you because I gave you the percentages, but in the lab, we're not going to have percentages. We'll be working with kilograms. Everything here is 5.47. So this is 6. So that's 5.47. So it's probably here, right? So you can come this way and that way, and you see that this is your center of gravity for the entire arm, the upper arm. Now, this is a very important procedure actually that we do to look at center of gravity when someone has an prosthetic, because it changes the balance, the weights, and that goes for upper and lower extremities. And one of the things that actually keep intimidating me actually is people when they have 2 of their lower extremities replaced by prostheses. So that is how this will change the center of gravity for the subject. A cool also application for this is when you design a wheelchair for people who have disability in the Paralympic, because that's also another issue when you design how would you design it to make sure that the center of gravity is stable. Now, remember, this is all simple because we have done percentage of weight. So here the y, the first one is 7, and then you do 4, and then you do 5, right? And you multiply it with the masses, you still have the masses, and you add them together, and you have your summation, divide by 1, and this is your 547. And if you check the solution, checks for us. Make sense? We good? So those are 2 ways to find the center of gravity of the human body. So we're not thinking about the center of gravity of a wheel or a bicycle. It's the human body that we care about. Right. Why is this important? This is important because it will help us in stability and balance when we design assistive technology or prosthetics or any robotics for the human body. We good? Make sense? Any questions? Alrighty. So let's get into the stability and balance. Now, there is a big difference between the two. People use it they replace each one with the other, but that's a big issue. So stability is the resistance to disruption of equilibrium, which means that you already have an equilibrium, right? And you're trying to resist the disruption of that equilibrium. That's called stability. Now, balance is the ability to control equilibrium and to change it. So if a ballet dancer actually, as she moves, she actually is controlling the equilibrium, right? By standing on, let's say, her toes. Does it make sense? So stability is different than balance. Do we agree on that? One of them is resistance, the disruption of the equilibrium to maintain it, and the other one is controlling the equilibrium. That's balance. Now, you play sports. So which one do you think that you are doing better? Or your sport, does your sport need more stability or does it need more balance? Each one is different, right? Some of them will have, can you think of a sport that needs more equilibrium? So for more control, let's say dancing, or that's need more control. What do you call the cheerleader? The cheerleaders, they need more control of their balance, right? Now, but stability, for example, athletic skill require mechanical stability. What do you call that when people on the 2 bars and they stand? Yeah, the parallel bars. That needs more stability, not more control. Does that make sense? What do you call the one that it has one piece and they jump on the balance beam? The parallel bar is the one that you swing around, right? And the balance beam is the one that you jump on. Now the balance beam is the one that you need more stability. Does it make sense? That one, the parallel bar, you need more control, which is balance. Yeah, so performing an point acquire excellent balance. Yeah, you need more balance when you do performing a task, right? Performing a routine. You need more balance in doing that. Is the difference between the two clear now? Yeah, you need to be careful when you use balance and stability when we assess mechanical performance of the human body. Now here's another thing which is important. We looked at the center of gravity, correct? We have something called the base of support. Now the base of support, it can be the center of gravity, but not all the time. So it's the area bound, that's the base of support. It is the area bound by the outmost region of contact between a body and a supporting surface. So if you are standing on the floor, right? See the areas of the two feet here. Now, this is going to be your base of support. Make sense? Now, and the thing is that if you are standing with your feet close to each other and someone tried to push you, you're going to fall quickly. But if you want to stop this, you increase your base of support by spreading the feet away from each other, and then you'll have a larger base of support, which gives you more stability, right? Does that make sense? You get more stability. Now, if you put your feet one in front of the other, you're trying to actually make the base of support in such a way that it will resist pushing you from the forward. Someone is pushing you in the frontal plane. Does that make sense? How we look at that? If you're standing on one foot, that's how it looks like. Now, what if you have you're standing on the toes, and you're putting your fingers in front of you, so you're pushing yourself on the front. Now your base of support is now a triangle, right? And each one of them actually giving you a way of supporting the body. Now the second one here, you have the two hands on the floor, the fingers, and standing on your toes. That's your base of support. So the larger base of support is the one with the 10 fingers and the toes on the back, and that will create a more stable, contact with the surface. Does it make sense? How we look at the base of support? So this is another important quantity that is important for stability, which is the base of support. So how can you increase stability? Because that's something we need to. You can increase stability by increasing the body mass, right? Because that's going to create larger weight. You can increase it by increasing the friction between the body and the surface of contact, and that's another experiment we're going to be doing, shortly, very soon. There's another way to increase stability by increasing the size of the base of support. See the different sizes that I showed you? Each one of them will have a different area, and the larger the area of the base of support, the larger or more stable the body is. Now, so increasing the base of support, as I told you, by spreading the feet away from each other, that will increase the base of support area, and then that will increase stability. And see the red dot here? The red dot here is a representation of the center of gravity. Now, if you tilt yourself horizontally toward one of the sides, you're pushing the center of gravity to that side, correct? Now that will make things even harder to destabilize from that end. Does it make sense? So if I'm leaning this way and someone tried to push me from that side, they're not going to be able to move me much. So horizontally positioning the center of gravity near the edge of the base of support on the side of the external force make it more stable. Does that make sense? We good with that? Okay. Now the other thing is that height. So if you've seen people playing basketball, do you see when they're in defense, they actually put the one foot in front and the other one back, and then they go down? Why do you think they go down? You lower the center of gravity, and once that is lower, that means it's more stable. Does that make sense? So we increase the mass, more stability. Increase friction, more stability. Move the center of gravity toward the line of action of the force, increase stability. And the third or the fourth one is by reducing the height of the center of gravity, makes it more stable. So vertically positioning the center of gravity as low as possible increase the stability of the subject. So the higher the center of gravity location, the greater the moment of torque. Remember that because we have a larger distance, you multiply the distance with the force, it will create more moment, and that can destabilize the structure. its motion creates about the support surface. Does that make sense? We good with that? Of how we look at this? Now, another example, lowering the center of, or positioning the center of gravity for people who play sports is in swimming. So swimmers position their center of gravity close to the front of their base of support when they're trying to jump forward, so that that give them larger acceleration, and that's going to help them in getting a better start because of the larger acceleration that they're going to get. So the center of gravity, whatever sport you're playing, you need to always be aware of the center of gravity and the base of support. And if you know how to control these two, you will increase acceleration and reduce the amount of energy you need to consume when doing a sport. That's in healthy situation. People with disability, it's a different situation because it's going to help you design assistive technology products for them to control that. So the shorter person will have smaller mass. So they would like to rely on the strength of the arms to push. Now, if you have a larger mass and you lean forward, that will give you more acceleration. Yeah. The mass dictates where the location of center of gravity. Now, depending on how the mass distributed is in the body is actually very important to look at. And if I keep noticing this, swimmers are they're selected now taller and thinner as opposed to what they used to. But they have not thinner. They're taller usually, swimmers, but they will have the waist up, a lot of muscle build, really a lot of muscle. Yes, compared to that's an interesting observation. But here's the thing: we have a swimming team, so we can take videos actually using our cameras and then come to Canovia. And the way that I'm going to use the segmental method, you will identify each player athletic, how they actually position their center of gravity and where. And then you can tell, well, we can design a training protocol that say, well, you need to move this a little bit backward or forward. And that's whatever doing it's wrong. You'll find people who have everything is good, but the execution of the technique is bad. And they can injure themselves. Yeah. Oh, yeah. And remember, see, when they have this, the base of support. Now, the wider the base of support, the more stable. You need to make the base of support small so that you can push yourself forward. And that's an important actually way of looking at it. Yeah. But it's about this. Yeah. We are looking at all the parameters. Okay. So in summary for this chapter, so I just copied this from the textbook because I like the summary of it. So rotary motion is caused by torque. We agree. Most of our movements are angular, a vector quantity with magnitude and direction, and to get the torque or the moment you multiply the force by the distance, and there's a direction. When a muscle develops tension, it produces torque at the joint or joints, that is crosses. So if you would like, that's why it's important. If you would like to assess forces in the body, we don't talk about forces, we talk about torques. And if you want to assess torques of the body, you look at the joints. That's the most important thing that we look at. And rotation of the body segment occurs in direction that result in joint torque around each joint. Mechanically, muscles and bones function as levers. We talked about them, class 1, 2, and 3. And we said in our body, most of them are class 3, where you have the force between the resistance and center of rotation. That is in most of our bodies. We said structured for maximum range of motion and moment speed, but require muscle force. Yeah, so we talked about that. The angles at which a muscle pulls on the bone also affect its mechanical effectiveness. Remember, because the angle, we said we have something stabilizing and we have dislocating forces. So that's the angle that we talked about. If you're doing this way and you're pulling, you're stabilizing. And if you're doing that, you're dislocating the joints. When a body is motionless, it is a static equilibrium. We talked about that. And the three conditions for static equilibrium: summation forces the x-axis equal to 0, summation forces the y-axis equal to 0, and summation of moments equal to 0. We're good? And then we said we have something called dynamic equilibrium. And we have, the skydiver, that example that we calculated. You need to add mass multiplied by the acceleration in order to have an equilibrium with these two. Okay, the mechanical behavior of the body is subject to force or forces is greatly influenced by the location. Remember when we did the mechanical advantage, that the length of the arm, all these kind of things. And that's something you need to make sure that you think of. And the different procedures are available to determine the center of gravity. We have the two ways: the balancing way, and we have the segmentation. That's what we did today. And body mechanical stability is resistance to both linear and angular acceleration, which is trying to resist change in the equilibrium. That's stability. Now, balance is trying to control stability. There's two different things. Okay, and then we talked about how can you increase stability. You increase the weight of the subject, you increase the base area of the base of support, you lower the center of gravity, right? And what I want from you to think about is, how can we apply this into something that you do routinely? This is kinetics, right? It's forces, moments. It's the torque and the forces. And then we look at stability and all the different parameters we go through. I will go next on Friday. We will start with another kinematic analysis, because that's another important topic we need to cover. We're good? Alrighty.